Hey, we're going to be covering Chapter 2.8, Graph Linear Inequalities in Two Variables. So these inequalities will take the form of ax plus by is less than c, and the less than can also be less than or equal to, greater than, or greater than or equal to. For the purpose of this example, I just used less than. So a, b, and c are all constants that are not zero. So for example, we could have 3x plus 4y is less than 5. And our a would be 3, our b would be 4, and our c would be 5. Now xy, so we could have a point 1, 2, is a solution of this inequality if it makes the inequality true when plugged in. For example, or actually let's use negative 2, 3 is what we're given. In this inequality, 8x plus 6y is greater than 2. So if we plug this in, we can see if this point is a solution. We get 2 is greater than 2, which is not true. So this is not a solution. So next we're going to be talking about graphing inequalities, and let's start off simply with a one variable inequality. And this represents a graph that looks like this on the right. And we have if you think about, rather than an inequality, we have y equals negative 3, that would just be a line, correct? It would just go right across here. That would be our line, y equals negative 3. But instead we have y is less than or equal to negative 3, which means that this whole area is less than or equal to negative 3. Therefore, the subject, or the area that is related to this inequality is a shaded area rather than a line. So anything in this area would be a solution to this inequality. For an inequality with two variables, we instead have a line that bounds our area. So this is our line, and again, if you think about if this were a simple 5x minus 2y equals negative 4, this would be our line, but rather we have 5x minus 2y is less than or equal to negative 4, so this entire area contains the solutions to our inequality. So we've already talked about absolute value in terms of graphing in previous sections, but this time we're going to be covering absolute value inequality. And I've taken this from page 135 of your textbook. So once we've graphed this, you may notice actually, based on this graph and the previous two, that we are using a dashed line to make our boundaries for our graph. And this is because we have greater than rather than greater than or equal to. So if it were greater than or equal to, this would be a solid line making our boundary for the shaded area. And this is because if you think about it, the greater than or equal to means that anything on this line is also a solution, whereas this is just a boundary line if there are not solutions, and therefore is dashed. So a solid line, once again, is for greater than or equal to or less than or equal to, whereas a dashed line is for greater than or equal to or less than, or just greater than or less than, sorry. So when further analyzing this graph, we can see that this concept is similar to that of the translating and transforming concept that we covered last section, and we can see this in the shape of the inequality. So if we think about this as just a simple absolute value equation, then we have our v that has been rotated about the x-axis, so normally it would look like this, but now it looks like this. And then it has also been, so the rotation is the negative here. The 2 means it has been shrunk, so it is not as wide as the parent graph. So rather than being like this, it has been shrunk. And then it has been moved to the right 3 and up 4 on the y range. So we can really apply what we know about absolute value graphs to inequality graphs.